Hello and welcome to section 2.5 on the chain rule. In section 2.3, we obtained the majority of our differentiation rules, and in section 2.4, we explored the derivative of trigonometric functions. In this section, we will develop the long-anticipated differentiation rule for composition. If you are unfamiliar with the composition of functions, stop and review section 1.3. Before the technical details, let's try and get an intuitive understanding of the derivative through composition. Cars have a certain fuel economy, an average miles per gallon. We can describe this relationship as m equals f of g, where m is in miles driven and g is in gallons of gas consumed. Fuel costs are variable throughout the year. We'll flip the price you usually see and report it in gallons per dollar rather than dollars per gallon. We can describe the relationship as g equals h of d, where g is the gallons of gas consumed and d is the price in dollars. How would we describe the cost of driving? That is, how do we connect the number of miles driven to the dollars spent? Your cost of driving depend upon your car's fuel economy and the fuel costs. Suppose I drive 300 miles on a 10-gallon tank. That is, 300 equals f of 10. And suppose where I happen to stop for gas was selling gas at $4 per gallon, or 0.25 gallons per dollar. That is, I spent $40, or 10 equals h of 40. How could we use h and f to describe the cost of driving? We use composition. Since m equals f of g and g equals h of d, we can substitute h of d for g to find that m equals the composition of f and h. That is to say, d is equal to 40. I spent $40 to obtain 10 gallons of gas. And with those 10 gallons, I drove 300 miles. Let's incorporate rates of change into this discussion. For fuel economy, the units would be miles per gallon, and for fuel costs, the units would be gallons per dollar. Suppose that the price of gas increases by 0.2 gallons per dollar in August, and you drove with more caution in August, causing your fuel economy to improve by 4 miles per gallon. How would you expect your cost of driving, the miles per dollar, to change? Working backwards with the units we have, if we multiply fuel economy change and fuel cost change, we obtain the units for the change in cost of driving. So with an improvement of 4 miles per gallon, and an increase of 0.2 gallons per dollar, we'd expect an increase of 0.8 miles per dollar in our cost of driving. Let's take another look at these units. We've just seen how average rates of change are multiplied through composition. We took the change for the month of August, an average, and we expressed that with delta for a change. Let's move away from that example to abstract variables. Suppose that y depends on x through the function f, and x depends on t through the function g. In terms of average rates of change, we're looking at the change of y with respect to t. Our example highlighted how average rates of change are multiplied through composition. But we are not interested in averages. We are interested in instantaneous rates of change, derivatives. In section 2.1, we emphasized how limits change the average into the instantaneous. Does that apply so smoothly here? Is it true that we can describe the derivative of y with respect to t through multiplication of the derivative of y with respect to x and the derivative of x with respect to t? Out of Leibniz and into more familiar notation, is the derivative of y with respect to t f prime of x times g prime of t? The answer is yes, and let us take a second to justify that. We're taking two functions, y equals f of x and x equals g of t, and we are assuming that they're differentiable. We're interested in finding the derivative of the composition, that is, the derivative of y with respect to t, or the derivative of f of g. We'll find this derivative through the limit definition. But instead of h, we'll talk about delta t, which represents the change in t. Since y is equal to the composition of f of g at t, our limit can be written as delta y over delta t. But we know that y depends upon x, and x depends upon t, so we can algebraically work delta x into the fractions. Because the function g is differentiable, it is also continuous, which means that as the change in t goes to 0, the change in x would also go to 0. Notice that the first limit is the derivative of f, and the second is the derivative of g. We began by assuming that these functions are differentiable. That means that both limits exist. So we were correct in using an equal sign, because we can split the limit over the product due to the smaller limits existing. And we obtained the derivative of our composition. We obtained an expression which is an alternate version of the chain rule. Let's manipulate this into an easier form. Since u equals g of x, the derivative of u with respect to x is g prime of x. Similarly, y equals f of u means that the derivative of y with respect to u is f prime of u. And since g of x is just a placeholder for u, we find that the derivative of y with respect to u is f prime of g of x. We make the replacement of dy over du and du over dx to obtain the chain rule. The chain rule describes how to take the derivative from the composition of f and g. We will call f the outside function and g the inside function. And the chain rule can be described as taking the derivative of the outside, being sure to leave the inside alone, and then you multiply by the derivative of the inside. Let's take the derivative of a function that I promised to derive back in section 2.3. Identify the composition. The outside is f and the inside is g. The derivative of sine x is cosine x, and the derivative of x squared plus 7 is 2x. Using the chain rule to find the derivative of y with respect to x, that is, the derivative of the composition f of g, we begin with the derivative of the outside, leaving the inside alone, and we multiply by the derivative of inside. If you like, you can do this in 2 steps. You take the derivative of the outside, leaving the inside alone, and then multiply by the derivative of the inside, which we have yet to take. This method allows for taking the derivative of more complicated functions. For example, a function which is constructed of multiple compositions. We take the derivative of the outside, leaving the inside alone, and multiply by the derivative of the inside, which we have yet to find, and will need to apply the chain rule a second time in order to calculate. Taking the derivative of the inside, we multiply that derivative to the existing answer, leaving the inside alone, and then take the derivative of the inside. We obtain a nasty looking derivative, but you want to get used to that. Not all calculations are going to end up pretty. We end with an application of the chain rule on powers of functions. This rule recognizes that the outside function is an nth power, and immediately uses the power rule. For example, take x to the 5th plus 4 to the 90th power. The outside function is x to the 90th, and the inside function is x to the 5th plus 4. We take the power rule on the outside function and then use the chain rule. In summary, we have filled our list of derivatives. We now have a derivative for every building block and the ability to differentiate all of their combinations. It takes some time to get used to the chain rule, so be sure to strengthen your understanding through practice.